it's very hard to talk about emerging pollutants after all these professors, especially Mirjana Miroladov, because she's very eloquent, and I'm young, still young. This is my first time with all this big audience to speak and be in front of these experts and lovely people. So, I'm Srđan Kovačević. I'm coming from the University of Novi Sad, Faculty of Technical Sciences, from the Department of the Environmental Engineering and Occupational Health and Safety and Health. And I will talk a little bit about the fate of emerging pollutants, especially pharmaceuticals, in alluvial groundwater of large rivers in Serbia. First of all, I want to say, like Professor Dinkić said, that in Serbia we are using above the 70% of the water supplies comes from groundwater, and 50% of groundwater we draw for drinking water supply comes from the alluvial groundwater sources. We can see that on this figure. That is data from the Statistical Office from Serbia. Also, something about the emerging organic contaminants. We all know that the contamination of water resources with thousands of micropollutants is becoming one of the key environmental problems, like we heard in many presentations today. And these terms do not refer only to newly developed compounds, but also to compounds newly discovered in the environment due to improvement of the analytical methodologies or methods. These recently discovered contaminants are present in the environment as a result of their expansion, but mainly due to the fact that they were not considered as contaminants before. On this side, we can see a generalized picture how the pharmaceuticals and their metabolites enter the municipal sewage system and aquifers from homes, health care centers, facilities, and farms. Also, since several pharmaceuticals residues are not completely removed during conventional wastewater treatment, we also heard today that, like we heard from Professor Norbert Preusinger and others, or is it case in Republic of Serbia where 50% of wastewater is only treated? From that percent, even less, because that treatment plants are not still working. And from that number, about 90% is secondary treatment. So the pharmaceuticals are not removing at all. On this slide, we can see the bank filtration scheme. As we all know, water is infiltrated and percolated through the aquifer. After that, the alluvial water is abstracted through the well, and after that, it is going to the water treatment if it is necessary. While groundwater is percolating through the aquifer is becoming a huge or big biochemical reactor, and the oil concentration wants to attenuate, and we want to meet the basic quality standard, or basic quality. We can track these bank filtration effects by many substances, or in this case we have an example of total organic carbon, like Professor already said. We can track bank filtration efficiency by TOC, DOC affection of removing micropollutants, in this case pharmaceuticals, removal or reduction of other substances, and greater safety in river accidents situation. On this slide we can see the picture of TOC, or total organic carbon, in Sava River. That are the data from the Institute of Jaroslav Černi from the year 2010. We see the great reduction from total organic carbon, like on slide. Within this research period from the 2009 until 2012, we did 122 samples for surface water and groundwater in the Republic of Serbia. 49 samples of large rivers or river basins in Serbia were analyzed. That are on Danube River, Novi Sad locality, Smederevo locality, Kovin locality, and Veliko Gradište. on Tisa River Titel, Velika Morava River, Ljubičevski most, and others. And also from 2010 until 2012, the total number of 73 groundwater samples from significant groundwater sources in the Republic of Serbia are included in analysis. Like Belgrade groundwater source, drainage system Kovin Dubovac, drainage system Knićani Čenta, groundwater source Trnovče, groundwater source Ključ, groundwater source Medijana Niš, and other groundwater samples. The selected pharmaceuticals were analyzed by solid phase extraction, followed by liquid chromatography, tandem mass spectrometry, like Professor Mila Lušić explained earlier, and that is described in the literature. Analyzed for the selected pharmaceuticals and sorption isotherms were accomplished in cooperation with the Faculty of Technology and Metallurgy TMF in Belgrade, and all relevant analyses regarding to the groundwater quality and quantity are completed in the laboratory for the physical, chemical, and biological water analysis at the Institute for the Development of Water Resources, Jaroslav Černi. The essential input data for the hydrogeological and hydrodynamic parameters and benchmarks were established based on these two projects. I will not read that. And in this slide, we can see the limit of detections and limit of quantifications for selected pharmaceuticals. We can note that there are different limits of detections and quantifications, and there are three groups of pharmaceuticals that were analyzed. First group of pharmaceuticals was analyzed continuously from the 2009 until 2012. That's trimetoprium, sulfametaxazole, azithromycin, doxycycline, erythromycin, bromazepam, carbamazepine, lorazepam, diazepam, diclofenac, metamizole metabolites for 4-aminoantipyrin, 4-FAA, and N-acetyl 4-aminoantipyrin, 4-AA. Second group was analyzed from 2009 until 2010, and six of them, paracetamol, amoxicillin, ampicillin, phenolbarbital, acetylsalicylic acid, ibuprofen, and others. And during that period, there were higher limit of detections and quantifications, so they were not detected. Maybe because of that, the third group was analyzed from 2011 until 2012. That are the cardiovascular pharmaceuticals, like that is listed in this table. That is one of the problems, like many of others said. That is a technology, that are the instruments and different limit of detection and limits of quantification. Next table shows the results for the analysis of all pharmaceuticals in surface and groundwaters. Just go back. We can see the percentage of the positive detection and concentration rate for detected pharmaceuticals. It's clear that from 25 analyzed pharmaceuticals, only 9 of them were detected, like it's shown in the table. For the purposes of the micromodel setup and next experimental research, we have chosen 4 pharmaceuticals that they are listed in this table, and the main reason for selection of these pharmaceuticals is detection frequency, occurrence in monitored wells, except trimetoprium, and their persistency. This picture also displays the percentage of the detection for selected pharmaceuticals in Danube River and monitored well BP12. We can see the percentage of detection is significantly higher in the Danube River. Now we can see the localities for modeling samples. The Danube River, as we all know, is the second longest river in Europe and one of Europe's most important waterways. It was about 2,850 kilometers from Schwarzwald in Germany to the Black Sea, and it is affected with about 80 million people. Collection sites for input data for the development of the hydrogeological and hydrodynamical micromodel and transport modeling are within the area of the municipality of Kovin. That are the localities at the first drainage line, the well BP12 and the two associated piezometers BP12P1 and BP12P2. Also, we can see the micromodel boundary that is about 300 meters wide and 160 meters long. This is just a picture from the field of that well and the construction of that well. And just to say something about that sector called Dubovac, it includes the settlements Dubovac, Gaj, Malo Bavanište, and Kovin, also known in Kovin Depression. It has an area about 177 square kilometers. This system operates from 1970 until now, and this well was built in 1980. It is located at the first line, as I said, and it is still operational. It has a capacity about 2 liters per second. The sediments of the uppermost porous aquifer and obstructing back filtrate are older quaternary and upper part of the deposits at the end of the late Pleistocene and Holocene deposits in gravel sand, and the lower elevated clay sediments in the upper part of the alluvial plain. Thickness of gravel sand deposits about between 1.5 and 20 meters. Shelf layer thickness is on average about 7.5 meters, and thickness of water-bearing layer is approximately 15 to 20 meters. Drainage well BP12 with accompanying piezometer BP12P1 and BP12P2 was screened in the groundwater at 3 to 4 meters below terrain elevation at a distance of approximately 350 meters from the Danube shoreline, but shoreline is moving slightly over the rear. And in drainage wells, the measurements were made with probe immersion in water to the level of the filter design, and in piezometers, the probe was dived to the filter structure after throwing at least 3 volumes of water from the piezometric using peristaltic pumps. Now we can see the ending results for the analysis on that section in Danube River and accompanying piezometers and wells. And based on the results of the analysis for the presence of selected pharmaceuticals in surface and groundwaters, we calculated the average concentration in Danube River and accompanying drainage well and piezometers. We can see that, according to the results, there is a strong evidence that there is a significant degrees of pharmaceutical concentration from the Danube River to wells BP12 and BP and accompanying piezometers. For the purpose of the model setup, we choose in the first phase carbamazepine, and his initial concentration is about 40 nanograms per liter, and the measured concentration in BP12P2 is about 4 nanograms per liter, and BP12P1 is 4 nanograms per liter. On this slide, we can see the results of the analysis for the sorption isotherms. They are determined for the purpose of 2 previously mentioned projects in cooperation with the Faculty of Technology and Metallurgy and Professor Lušić. Results for the carbamazepine linear coefficient of sorption are shown in table 3. The results obtained for the Freundlich sorption coefficient are translated into linear form because of the sorption occurs linearly for small concentration of pharmaceuticals. In this case, 40 nanograms per liter. In this case, that is 200 nanograms per milliliter. Main processes which take place, as all we know, which take place in aquifer are dispersion process, exchange process between the solid phase and the liquid phase, degradation process, and others. We can see the continuity equation for the flow of water in the aquifer. That is one of the most important equations. And the second equation is the continuity equation for the migration of substance in the aquifer. Finally, we can see the results of this model. First of all, I want to say what is the aim of this study. It was to examine, the main aim was to examine the occurrence and behavior of selected pharmaceuticals and their residues during passage through the river bed and aquifer sediments. And we also wanted to correlate those results with the model for the transport of pharmaceuticals in alluvial groundwater by application of groundwater model low viscous software package. As a result, we calculated the gradation kinetic of analyzed pharmaceuticals, which was approximately determined based on the hydrogeological and conditions and affinity for sorption, which were calibrated in the model. Example is displayed as a 2D model setup. First of all, we set up the steady state conditions for surface waters and groundwaters, hydrogeological conditions, and the result is that groundwater flow is about 90% from the river Danube, while the result of the calculation indicates that the path of groundwater from the Danube River to the drainage well, BP12, is within the framework of 30 to 40 miles. That is the ideal case without all these mechanisms. Also, it indicates that the pharmaceutical concentration attenuation from hinterland or backland or upperland is approximately 10%. So we have attenuation or dissolution of pharmaceuticals from the backside. As a result of the transport method, the relevant current image and isolines of alluvial groundwater of concentrations are given, as we can see on this picture. And one of the conclusions was that the linear sorption coefficient value in transport model calculation are significantly smaller than the sorption coefficients based on experiments. These differences are probably a result of the composition of the aquifer and different particle size in water-bearing layer along the model boundaries that affects the sorption kinetics. And there are different sorption mechanisms. Degree of carbamazepine degradation is very low, similar like the results showed in the literature, since breakthrough curve, as we can see, has shown that after approximately 20 to 40 years, we could expect carbamazepine breakthrough concentration of only 2 nanograms per liter, and the same concentration is measured. So after 20 years, we can have the concentration on that well BP12 of 2 nanograms per liter. So that means that that carbamazepine was inputted maybe a few years ago. So it's accumulating. It's the constant input in the system, and it's accumulating, it's very low degradable, and it's not degrading, so he sorbing and then desorbing and then gets to the well. And finally, the conclusions, as I already said, but I must repeat, analyze data for the detection of pharmaceuticals in major rivers and groundwater sampling localities in Republic of Serbia showed that there is a significant decrease 3 to 5 times in the initial concentration of pharmaceuticals during passing through the water-bearing layer, even more. Obtained data are showing that the benefits of bank filtration and artificial recharge during passage through a few layers with different aerobic condition degree. And in this case, the result for carbamazepine linear sorption coefficient value in transport model calculation are smaller than the sorption coefficients based on the experiments. In some cases, 5 times smaller. We also developed new methodology for assessment and determination of micropollutant transport and degradation kinetics, and this research is still ongoing in progress, and it's part of my PhD thesis. I would like to thank my mentor, Professor Dimkic, and his associates, and and colleagues, Professor Milenko Pušić and PhD Dragan Vidović for helping me on this paper, and also I would like to thank you, all the people who participate in this research. Thank you very much.